Hi guys, so today I will be talking about oxidation at the benzylic position of aromatic compounds and the reduction of aromatic compounds. So first of all, let's define what the benzylic position is. The benzylic position is defined as the carbon atom immediately adjacent to the benzene ring. So like right here is the benzylic position, because it is the carbon immediately adjacent to the benzene ring. So this carbon over here. And my first example is an alkyl benzene. And basically, if you add some sodium dichromate, which is right here, some acid, any type of acid, can be sulfuric acid, HCl, and some heat, you can oxidize the side chain to a carboxylic acid alkyl functional group. So this would be my product. So basically, the benzylic position, the benzylic carbon, is getting oxidized to a carboxylic acid, as you can see. So our next example is going to be butylbenzene, and we're going to react this with sodium dichromate again, some acid, and some heat. And you don't have to use sodium dichromate. You can also use potassium permanganate with some base and some heat to oxidize the alkyl side chain to a carboxylic acid. So we're going to do the same thing. We're going to find our benzylic carbon, which is right here. And now we're going to oxidize the alkyl side chain. And as you can see, it doesn't really matter how long your alkyl side chain is, you're still going to get a carboxylic acid, and the reaction is still going to occur at the benzylic position. So our product is So both of these products are the same, even though the alkyl side chains were different. So it doesn't really matter how long it is, because the end point really is that it's going to oxidize at the benzylic position. So yeah. And now let's do another example. So I'm going to use sodium dichromate again because that's my favorite oxidizing reagent. And we're going to use H2SO4 instead of a generic acid. And so we have tert-butylbenzene here. And when we react this with sodium dichromate, heat, and sulfuric acid, we get no reaction for this. And this is because there is no benzylic hydrogen present at the benzylic position. So our benzylic position is right here. And there are 3 methyl groups attached to this carbon. So there's no benzylic hydrogen, like there's no hydrogen there. If you look at the other examples above, there is a benzylic hydrogen here and a benzylic hydrogen here. So this is why the first 2 examples were able to be oxidized by this reagent. However, there's no benzylic hydrogen present at this carbon, so therefore no reaction occurs. So now on to our next example. So here we're going to use potassium permanganate, and some acid in our second step. Let me just draw this a little longer. Okay, so our product for this reaction is also no reaction, and this is because there is no benzylic carbon in this molecule, nor is there a benzylic hydrogen, since there's no benzylic carbon or position. So basically, as I said before, you can also use the reagents potassium permanganate, water, heat, and acid to oxidize your molecule. So now I will be discussing the Birch reduction. I won't be focusing on the mechanism, but more and more products will be synthesized. So if you have a substituted benzene ring, as shown here, with a substituent on it, and you add sodium, ammonia, and an alcohol, the substituent is going to affect which carbons are being reduced. So basically, if you have an electron withdrawing group on your ring, the carbon that's bonded to the Y substituent is going to be reduced. If you have an electron donating group bonded to your ring, the carbon bonded to that substituent is not going to be reduced. So let's do an example. So I'm drawing a benzene ring with an ester on it, and this ester is an electron withdrawing group. The partial positive charge, it has a partial positive charge, and it's going to withdraw electron density from the ring. So we're going to react this with sodium, ammonia, and an alcohol. So since this is an electron withdrawing group, we know that the carbon that's bonded to the Y substituent will be reduced. So basically, we're going to get this product. Since the carbon bonded to the Y substituent is being reduced, since the substituent is an electron withdrawing group. So like comparing the two products here above, they're like the same for the electron withdrawing group. The only thing that's different is the electron withdrawing group present. You know, like Y can be any electron withdrawing group, but the benzene ring, like the format of the benzene ring, remains the same, if that helps you remember it. So we're going to do another example. And this is an electron donating group. The oxygen has lone pairs and it can donate electron density to the ring. So we react this with sodium, ammonia, and an alcohol. And these are the reagents that you will always use for Birch reduction, always. And so the product we're gonna get is this. So since we have an electron donating group, the carbon on that substituent will not be reduced. So if we compare the electron donating group product above to this one, it basically has the same format. Like, you know, the benzene rings have the same format. The only thing that's different, that may be different, is the Y substituent placed on that group. So now we're going to move on to the final example of the Birch reduction. And here is our starting product. And in our starting product, we have two electron donating groups. So since we have two electron donating groups, we know that the carbon bonded to the substituent, which is the electron donating group, will not be reduced. So our molecule is gonna look like this for the final product. So basically, as you can, if you're comparing the electron donating group products, the benzene rings are very similar, even if you have two substituents on your ring to begin with, like the last example, they still have the same generic format. The only thing that's varying is the substituents. As you can see here, the only thing that's different is the substituents being placed. But yeah, so basically what you can take away from this is that whenever you have an electron withdrawing group on your ring, the carbon that's bonded to the electron withdrawing group will be reduced. If you have an electron donating group bonded to your ring, the carbon bonded to that substituent will not be reduced. And the reagents you'll be using in the Birch reduction will always be sodium, ammonia, and any type of alcohol whatsoever. And comparing the substituents from starting material to product, they always remain in the same place, always. And that's it.